Hello everyone, my name is Archon Ganguly, and in this video I'm going to talk about distributed event streaming architecture in a multi-region context. A multi-region setup on AWS supported by ROSA, that is RedHat OpenShift on AWS. It is a fully managed RedHat OpenShift offering jointly supported by AWS and Red Hat. At the end of this video, you will understand about the need for multi-region Kafka clusters, the physical operational model on AWS with ROSA, how Kafka clients, producers, and consumers discover and interact Kafka brokers in a multi-region setup, and then finally the steps to implement the architecture. Apache Kafka is a popular distributed event streaming solution, and if set up right, it provides durability and availability and supports compliance and legal requirements. Here you find a pattern which talks about cross-region replication for geo-proximity and lower latency to the end customers. We have three different regions, Ohio, Frankfurt, and Singapore, each having its own Kafka cluster. A customer profile is divvied up into two kinds of topics, one which holds the PII information and the other one the non-PII information. We are replicating the PII topic across the world, and by virtue of that, we are ensuring that the end customer is getting lower latency as far as access of non-PII information is concerned, such as order details, buying preferences, profile preferences, and so on. The next pattern, which is similar to the first, but this talks about a hub-spoke replication model. So let's consider an enterprise is having its global data lake in Ohio, and the non-PII data is replicated across the world to the Ohio region only. And once the non-PII data is available in the Ohio region, streaming solutions such as Apache Flink could be used to process the data and be made available in the data lake for further analytics. This pattern can also be applicable for an active-active failover setup with respect to a disaster recovery scenario. For that, you need to have all topics to be mirrored out from all different brokers to a dedicated region. So for example, if you want to have an active-active between Asia Pacific and Singapore and Ohio, then all topics have to be replicated across the two clusters. So as we discussed, there are several key architectural patterns, whether it is about cross-region replication to support geo-proximity for worldwide consumers, or setting up a hub-spoke replication model to support the ingestion into a global data lake, or it is about active-active failover setup in case of disaster recovery scenario. And also, you can use Kafka replication for data migration use cases wherein you want to migrate data in a hybrid cloud or in a multi-cloud setup. But the fundamental design pattern behind replication is asynchronous mirroring. One such tool which supports asynchronous mirroring is Kafka MirrorMaker. So you can configure your access control for the producers and the consumers using TLS, while the producers write to the commit log. Commit logs live in partitions of a Kafka topic in the source cluster, and the MirrorMaker connects to the source broker, consumes from the partitions of the Kafka topic, and then finally publishes it to the Kafka cluster, which is the target Kafka cluster. So let us take two regions. We have our hub in Ohio and spoke in Singapore. We would have ROSA clusters on both the regions, and Kafka clusters will be hosted on it. The replication between the Kafka clusters will be through global AWS network without traversing the public internet. So as we discussed, here we have two regions. For brevity, let us consider single availability zone setup in the regions. We provision the VPCs and have the ROSA clusters in each of those regions deployed. Each ROSA cluster has its master nodes, infrastructure nodes, and worker nodes. The worker nodes are where our AMQ Streams clusters run, and the brokers in the Kafka clusters are backed by internal load balancers. And we are going to talk about the whys and hows of the internal load balancers in the next few minutes. So while we have the two regions set up, the regions needs to be connected. And one way of connecting the regions is via TransitGateway. TransitGateway VPC attachments are to be configured with specific subnets where the worker nodes are placed. The TransitGateway peering connections are raised from one region, let's say from Singapore, and it requires to be accepted in the AWS console from the other region, that is in Ohio. And the TransitGateway route tables is where the inbound traffic from both the regions are configured with the right CIDR block of the other region. The alternative could have been to do the setup with VPC peering, but VPC peering doesn't really support transitive peering, which means that only directly peered VPCs can communicate with each other. And if you have overlapping IPv4 or IPv6 CIDR blocks, then it doesn't really work. And it becomes all the more challenging as the number of peered VPCs grows. So in this hub-spoke model for TransitGateway, it simplifies the management at scale because VPCs only need to connect to one TransitGateway per region to gain access to the ROSA AMQ Streams clusters in the attached VPCs. One thing to note, the TransitGateway has an hourly charge per attachment in addition to the data transfer fee, and unlike VPC peering, TransitGateway being an additional hop may cause a relatively more latency. Having completed the TransitGateway and peering connections, the MirrorMaker that would be in the Singapore region needs the VPC where it is running to be associated with the Amazon Route 53 private hosted zone. The MirrorMaker in Singapore will be configured to have the source bootstrap server as found in the Route 53 record set. When the mirroring happens, it goes via the Route 53 and then is propagated through the internal load balancers down to the individual brokers. So let us talk about how Kafka brokers are discovered. Kafka has its own discovery protocol. When a Kafka client is connecting to the Kafka cluster, it first connects to any broker which is member of the cluster and asks for its metadata for one or more topics. The metadata contains information about the topics, their partitions, and brokers which hosts these partitions. All brokers should have this data for the whole cluster because they are synced through Zookeeper. Therefore, it doesn't matter to which broker the client connected at first, all of them will give the same response. Once the metadata is received, the client uses the metadata to figure out where to connect when it wants to write or read from a given partition. The client will use the address from the metadata to open one or more new connections to the addresses of the brokers which hosts the particular partitions it is interested in. Now, let us talk about how we connect from inside the same OpenShift cluster to an AMQ Streams Kafka cluster. So with Kafka, as we know, it has its own discovery protocol. We do not need the clients to figure out the API address from the OpenShift API. We just need to configure it and the advertised addresses and the clients will discover it through the Kafka metadata. But there is even one more better option, which is used by RedHat AMQ Streams, that is for stateful sets, which AMQ Streams is using to run the Kafka brokers. You can use the OpenShift headless service to give each of the pods a stable DNS name. AMQ Streams is using these DNS names as the advertised addresses for the Kafka brokers. So with RedHat AMQ Streams, the initial connection is done using the Kubernetes service, the Bootstrap service, to get the metadata. And then the subsequent connections are opened using the DNS names given to the pods by another headless Kubernetes service that we discussed just now. Now let us talk about the Kafka clients that are outside of the ROSA cluster, that are trying to access the Kafka brokers running inside the ROSA cluster. In our case, the Kafka client is a MirrorMaker that is deployed in the remote AWS region, Singapore. One of the methods to access the cluster is through load balancers. Since none of the common load balancing services support Kafka protocol, AMQ Streams always use layer 4 load balancing. Since layer 4 works on the TCP layer, the load balancer will always take the whole TCP connection and direct it to one of the targets. That has some advantages. You can, for example, decide whether TLS encryption should be enabled or disabled. To give Kafka clients access to individual brokers, AMQ Streams creates a separate service with type load balancer for each broker. As a result, each broker will get a separate load balancer. Despite the OpenShift service being of load balancer type, the load balancer is still a separate entity managed by the cloud provider, in this case AWS. And a typical Kafka cluster with n brokers will always need n+1 load balancers. Now, as per the general definition of a load balancer, it is something that distributes incoming traffic across multiple targets. However, as you can see from the diagram, the per broker load balancers have only one target and are technically not performing load balancing. While that is true, but in most cases, the actual implementation is a bit more complicated. When OpenShift creates the load balancer, they usually target it to all nodes of the cluster, and not only to the nodes where your application is running. That means that although the TCP connections will always end on the same node in the same broker, they might be routed through other nodes of the cluster. When the connection is sent by the load balancer to the node which does not host the Kafka broker, the kubeproxy component of OpenShift will forward it to the right node where the broker runs. And this can lead to some delays, since some of the connections might be routed through more hops than absolutely necessary. So to wrap up, as far as the Kafka clients are concerned, including the MirrorMaker setup that we have in Singapore, it will use the Bootstrap load balancer address for the initial connection. And then it will subsequently use the individual broker specific load balancers to reach out to the brokers. There are other ways to connect to the Kafka cluster running in ROSA. The alternatives are OpenShift routes and as well as ingress. We are not going to cover those two in this video, but in some other video in future. So talking about internal load balancers, let us do a quick review of the listener setup of our source Kafka cluster. Like many cloud providers, AWS differentiates between public and internal load balancers. The public load balancers will get a public IP address and a DNS name, which will be accessible from the whole internet, while the internal load balancers will only use private IP addresses and host names and will be available only from certain private networks, such as from other machines in the same AWS VPC. Now, we want to share our Kafka cluster, our source Kafka cluster, running in the Ohio region with that of the MirrorMaker, which is running in the Singapore region. And we already had our VPCs connected via TransitGateway. So in this case, internal load balancers might come handy. Now, OpenShift always uses a load balancer type as public by default, and we can use special annotations to indicate that the given Kubernetes service with load balancer type should have the load balancer created as internal. As indicated earlier, we will be leveraging Route 53 that will use those annotations on the load balancer type services. AMQ Streams allows us to assign these annotations through the Kafka custom resource using a field called DNS annotations. And the DNS annotations allows you to configure the annotations at a per broker level as well. So how would you go about and perform the setup that we have discussed till now? It essentially consists of 7 steps. The first one is where we go ahead and set up the networking prerequisites for inter-region connectivity. Second, we provision the ROSA cluster in the 2 separate AWS regions. Third, we create a namespace, let's say with a name called AMQ Streams, and then provision the RedHat AMQ Streams operator. Next, we create the source Kafka cluster and the target Kafka cluster. Then we configure the Route 53 and configure cross-region DNS resolution. After that, we deploy the Kafka MirrorMaker in the target cluster. And finally, we deploy the producer in the source cluster and the consumer in the target cluster. So join me in the next episode where I will do a follow-along video of these 7 steps.